Since the launch of revolutionary models like ChatGPT and its various versions, the world has entered a new era of artificial intelligence. Generative neural networks capable of writing texts, creating images, and programming demand colossal computational resources. Against this backdrop, NVIDIA has seen explosive growth with its GPUs, which have become the gold standard for training and deploying neural networks. In just the past year, the company's revenue in the data center segment, which includes GPU sales for AI, has grown by tens of percentage points. Amid the AI boom, NVIDIA has become the new oil of the digital age. Its chips serve as the foundation for developing and operating neural networks, from chatbots to computer vision systems and autonomous driving technologies. AI increases energy demand in the US. According to research from the University of California, Berkeley, data centers in the US are consuming more electricity. The reasons include the growing number of servers with GPUs since 2017 and increased demand for AI services. The share of data centers in total electricity consumption, 2018, 1.9%, 2023, 4.4% 2028, forecast 6.7% to 12%. This means that by 2028, data centers will consume 74 to 132 gigawatts of electricity annually, assuming average utilization rates. 1 gigawatt equals 1 million kilowatts of electricity. Future forecasts are challenging, as overall energy demand will rise due to electric vehicles, localized manufacturing, hydrogen technologies, and building electrification. The ChatGPT 003 model, the O3 model from ChatGPT, represents an advanced development aimed at tasks requiring deep analysis and step-by-step logical reasoning. Its improved architecture is expected to effectively process complex data. However, no one except the developers has seen it yet. Everything so far is just announcements. For now, we have to take OpenAI at their word. High performance requires significant computational resources, which may become a barrier for small and medium-sized businesses without access to cloud infrastructure. Moreover, at this stage, the models are only available to researchers under a testing program, limiting their application. Nevertheless, testing has already demonstrated impressive results. The O3's excellent performance is in its GPQA Diamond test, where it achieved 87.7% accuracy on PhD-level questions in biology, physics, and chemistry, surpassing its predecessor, the O1, which achieved 78% accuracy. The GPQA, graduate-level Google-proof Q&A benchmark, is a dataset comprising 448 multiple-choice questions crafted by domain experts in biology, physics, and chemistry. These questions are designed to be exceptionally challenging, with experts holding or pursuing PhDs achieving approximately 65% accuracy, while highly skilled non-experts with unrestricted internet access attain only about 34% accuracy. For example, question from GPQA, methylcyclopentadiene, which exists as a fluxional mixture of isomers, was allowed to react with methyl isoamyl ketone and a catalytic amount of pyrrolidine. A bright yellow, cross-conjugated polyalkynyl hydrocarbon product formed. How many chemically distinct isomers make up the final product, not counting stereoisomers? This question requires a deep understanding of organic chemistry, specifically reaction mechanisms and isomer enumeration. Such questions in the GPQA are intended to assess the reasoning and problem-solving abilities of both humans and AI systems in complex scientific domains. The O3 model also showed excellent results on the ARC-AGI test. The ARC-AGI Artificial General Intelligence Test is designed to test AI for its suitability for performing tasks that go beyond the standard dataset. It is a combined exam of questions on mathematics, science, and logic, where it is important not only to give the correct answer, but also to demonstrate the ability to think. Success in ARC-AGI is a step towards creating artificial intelligence that can solve problems as effectively as a person. What is the difficulty of this test? ARC-AGI is designed so that models cannot prepare for the questions in advance. Each test includes tasks that are not found in textbooks. Logic puzzles. How many ways are there to connect nodes in a graph with a given number of edges? Mathematical equations. Find the probability of an event in a problem that requires manual calculations. Scientific experiments. What result can be expected from a reaction if the conditions have changed? These questions challenge AI to understand the context, analyze the problem, and come up with a solution. In this test, the O3 model achieved a stunning 87.5% correct answer rate. In comparison, previous versions of the O1 model achieved only 25 to 32%, highlighting the giant leap in technology development. The O3 model has shown that artificial intelligence can perform tasks at an expert level and sometimes even exceed human capabilities. However, this does not come for free. Its success requires more computing power than its predecessors. The main takeaway here is that O3's improved performance comes with a significant trade-off: higher costs during inference. As noted in a blog post by Clark, this advantage stems from O3's ability to leverage test-time compute, enabling it to convert computational power into better outcomes for certain problems. However, this also means that the cost of operating AI systems has become less predictable. In the past, the expense of running a generative model could be estimated by analyzing the model itself and the resources needed for output generation. The logarithmic x-axis on the accompanying chart highlights this disparity, and some may find it striking. For example, the high-performance variant of O3 required over $1,000 worth of compute per task. By contrast, O1 models operated at approximately $5 per task, and O1 Mini achieved the same for mere cents. François Chollet, the creator of the ARC-AGI benchmark, highlighted in his blog that achieving O3's remarkable 88% score required about 170 times more compute than a high-efficiency version of O3 that scored only 12% lower. The high-performing version consumed over $10,000 worth of compute to complete the ARC-AGI test. This cost makes it impractical for competing in the ARC prize, a contest where no AI model has yet managed to surpass the ARC test. Nevertheless, Chollet emphasized that O3 represents a significant advancement in AI. O3 demonstrates an ability to adapt to entirely new tasks, potentially nearing human-level capability in the ARC-AGI domain, Chollet remarked. Of course, achieving this level of generalization comes with an enormous price tag, making it currently uneconomical. Humans can solve ARC-AGI tasks for around $5 per task, while expending only pennies in energy costs. We've tested this ourselves. While it's too early to draw definitive conclusions about the pricing, especially given the rapid decline in AI model costs over the past year, these figures underline the immense computational demands of pushing performance limits in AI. OpenAI has yet to disclose O3's actual cost, but these initial metrics highlight the steep requirements for even incremental improvements. This raises critical questions. What is the intended application of O3? And how much additional compute will be necessary for future iterations, be it O4, O5, or subsequent reasoning models, to surpass the current benchmarks.